Please go ahead. Thank you.
So, hello everyone. So today's lecture is the second of the workshop on QKD. And we did last time some classical cryptography, and we saw the problems with it. And today we will see that what quantum characteristics are useful for quantum key distribution. First, I'll just relate it to what we did last time and from where we want to introduce quantum in our system. And those quantum characteristics that we will be using that are fused in QKD are in fact the no cloning theorem and then the Measurement process for orthogonal, non-orthogonal states. And then I'll introduce the BB84 QKD protocol, right? The first of QKD. So the QKD is in fact the quantum key distribution. So I have just taken the slide from yesterday's lecture in which we saw a symmetric cryptography, classical cryptography, which is a symmetric one, in which there was a plain text message M, and it was to be encrypted using an encryption machine, and was then sent to the produce a ciphertext using the private key, which is EM, and then send to the receiver who decrypts it using the decryption and gets the plain text back, right? So this is how it goes using this decryption. EM is the encrypted message, applying the decryption on it to get the message back. And the key has to be used the same between the sender and the receiver. So they have to somehow have the same key shared between them. So we look for some cipher, right? This ciphertext, which is to be produced, it should be some known cipher, right, between the sender and the receiver. So everybody should know it, how to encrypt and decrypt the message. So there was I talked about one-time pad, which is a Fernlem cipher, and it's a completely secure cipher. So it's a very simple one. So you have a message, right? You convert it into bits, and then you have a key with it, and the cipher is this, that it just takes the addition modulo 2 of the message and the key bit by bit. Okay, so you take one bit of message, so 1 plus 0 would give you 1, 0 plus, so addition modulo 2 is you just add them up, M and K. So 1, so you just take this M and 1 and 0 and add them up. It's 1 divided by 2, and the remainder is your answer. So 1 divided by 2, the remainder is 1. So this will be your cipher, the first bit of your cipher. Then you take the second bit of message, second bit of key, add them up, divide by 2, and this way you create the whole cipher. Now this cipher, as we talked yesterday, is impossible to break. It is mathematically proven to be secure, but there are certain conditions, right? It is impossible to break if and only if the key should be as long as the message, key should be random, and key should be used only once, and key is completely secret, right? So the problems that we discussed last time was this, that key has to be as long as the message, which means that if you have to send several messages, you have to have a long string of key to be used with it. Then key should be totally random, right? So there should not be some sequence in the key. So every time you have to have a random bit string of key, and it should be used only once. You cannot use the same key to encrypt two different messages. So which is again a problem, which means that every time you have to send a message, you need a new key, which means that if the parties can, so the last thing, of course, is that you have to keep it completely secret between the sender and the receiver. So anybody who gets this key K can decipher the text. How can they decipher? As I told last time, you can decipher it by using just the C plus K again, and it will give you the message back. So all these requirements to meet for the key is this, that the key, every time you have to send a message, you have to create a new key. So there should be some mechanism to generate the key readily, which means that whenever you want to generate the key, you should be able to do that. Otherwise, it's not practical for the two parties to meet and share the key. If you can do that, they can in fact share the message. So it's of no use than using this cipher. So there should be a mechanism to distribute the key. And this is what quantum key distribution is about, to distribute the key through the open channel in such a way that it is secret. And for this, we have to use the quantum characteristics. So let's go through them. First thing is the quantum bit, which is to be used in this. The quantum bit, as you would have known by now, just let's see this again, that there is a classical bit which has just two possible states. One is 0 and and the other is 1. But the quantum bit, it can exist in superposition of 0 and 1. For example, it can have a state 0 plus 1 over under root 2, right? Which is a superposition of 0 and 1. So you can think of the quantum states to be the points on the sphere, right? Which is a Bloch sphere. Every point on the Bloch sphere, on the surface of the sphere, is a quantum state. And I can write a journal quantum state in this way, that my state can be written in the state vector, which is alpha 0 plus beta 1. So this 0 and 1 are the qubit values that we are using over here, the 0 and 1. So they can exist in any superposition state. So if alpha and beta are 1 over under root 2, it will be this particular state, right? Which lies here on this point on the Bloch sphere. And any other point, for example, this point is 0 minus 1 over under root 2. And same way, since there are infinitely many points on the surface of the Bloch sphere, there are infinitely many states possible for a qubit. And if you measure a qubit, then of course you will get state 0 with, so the measurement would lead to measuring this qubit, you will get state 0 with alpha modular square probability, and you will get the state 1 with probability beta modular square, right? The state 1 with beta modular square probability. So this is how the qubit is. So whenever you measure it, it will collapse into one of the two states. So otherwise it's in superposition, right? Okay, so the no cloning theorem, as I said, that we'll talk about some quantum characteristics which are useful in QKD. So the first thing is this no cloning theorem, which says that you cannot clone an unknown quantum state. And what is meant by clone? Clone means that you have to make a copy of a quantum state, make a copy keeping the original, okay? So this is necessary, that you have to keep the original. And then an important thing is that we are talking about an unknown quantum state, right? Which means that if you do not know what the state is and you want to copy it in such a way that you keep the original, then how it goes, right? And what quantum states are there which we need to copy, which we want to copy or not, right? So let's just see that why we are claiming that you cannot clone an unknown quantum state. What is meant by, in fact, cloning? Is it really possible to make a clone of an unknown classical state? So classical bits, as I said, they can be 0 or 1. So there's a simple circuit which can in fact clone, make a copy, keeping the original, right? So which can make a clone of an unknown classical state. So a classical bit in the state 0, you can use a control NOT gate for this. So where your control bit is the one which you want to copy, right? And your target bit is always in the state 0, right? So for example, so this is your control bit. You want to copy a state 0. So your control bit is in the state 1, in the state 0, and you apply control NOT. So what you will get from this circuit, so you will get the 0 over here, and this, of course, control NOT, it will remain 0, right? What if you want to use so you have a machine, right, which you claim that it can clone an unknown quantum state, so unknown classical state. So which means that if the state is not known, let's take the state to be 1 rather than 0, it should make a perfect clone of that as well. So I keep it, this is the state, this is the bit I want to clone, and this is the bit which is in the state 0. So if I apply control NOT, my control would be in the state 1, and my target will flip to the state 1, right? So I have kept the original and I have made a perfect copy of it on this target qubit. I have kept the state 0 over in the first case, and I have made a perfect copy in the other. So the same cloning machine, the same copying machine has made a perfect copy of an unknown classical bit, whether it is 0 or 1, right? So our copying mechanism doesn't change with the bit. So we just apply this circuit and we get a perfect clone. So it is not, it is always possible to clone an unknown quantum classical state. Now, what do we mean by a clone? What are the problems if we try to do a clone of an unknown quantum state? as I said, that a quantum state can be anything like psi is equal to alpha 0 plus beta 1. And being unknown, it means that we do not know what alpha and beta are, right? So it can be anything, any point on this Bloch sphere, right? So we do not know what it is. Of course, there are some fixed values. It's a fixed quantum bit, but we do not know what the values are. So what happens is that when we try to make a clone of such a state, let's see that we have devised a cloning machine which can make a perfect copy of the 0 and 1 states, which means that if I have a 0 state and I want to make a perfect copy, so I have something like a blank state, and I have a cloning machine which is in the state F, right? And then I apply the cloning process on it. So I'll get I should keep the original, right? I keep the original, which is this first one, 0. I should make a copy of it on the blank copy, which is 0. And I should keep and then my cloning machine will go in some state, let's call it F0, right? Which is different from the initial state F. And this cloning machine is capable of doing a copy of the state 1 as well. So I have state 1, I have the blank copy, I have the cloning machine in some initial state F. It undergoes the cloning process, keeps the original, which is the state 1, makes a copy of it on the blank copy, which means that it should be in the state 1, and my cloning machine will be in some state F1. Okay, so this cloning machine is capable of making a perfect copy of 0 and 1. So now let's see if the state is something else. It's not really 0 and 1, then what will happen? So the state is an unknown state, which is alpha 0 plus beta 1. And I use this same cloning machine, which is in the state F, to clone this. Okay, so how will it go? So after the cloning, it will be alpha. So I have to apply the linearity of quantum mechanics, which means that if there is this sum, so it should go as, so let me just add one more thing over here. There's a blank copy as well on which I want to make a clone. So there's this B and F. So I have alpha 0, B and F for this, and I have plus, beta, and 1, and the blank copy, and F. Okay, so these two are in fact equal from here. So then after the cloning process, it goes like this. It is, since it knows how to make a clone of 0 and how to make a clone of 1, so it will go exactly like it goes here, right? So for the first case, first term, alpha 0, beta 1, after the cloning process, it will become alpha 0, clone on the blank copy 0 as it knows how to do it, and this cloning machine in the state F0, just like the first case over here, right? So then I have beta 1, the copy on the blank one, which is 1, and the cloning machine goes to F1. Okay, so this is what I will get. But is it really a clone that we wanted? So if I want to make a clone of this alpha 0 plus beta 1, and with some cloning machine, not necessarily this, but with any, or which claims to have and to be able to make a copy of it, it should be something like this. It should go like alpha 0, it should keep the original, which is alpha 0 plus beta 1. On the blank copy, it should make a copy like alpha 0 plus beta 1, and the cloning machine should be in the state something, right? Which is F alpha or anything, F prime, let's call it. So it is not the same as this state. You see, if you just open it up, it will be alpha 0, 0, alpha 0, 0, blank copy 0. And in fact, it is alpha square and plus alpha beta, and of course the F prime, and plus, if I just write F prime at the end, it will be alpha 0, 0 plus alpha beta 1, 0, 1 plus alpha beta 1, 0, and plus beta square 1, 1. And with all of this, my cloning machine to be in the state F prime, which is not equal to this, right? So these two situations are not same. okay, what we expected from a cloning machine. It should keep the original and it should make a perfect copy on the blank one, which should look like this, right? Which in fact translates into this, into the last line. But this is not what we are getting. So our cloning machine was capable of making a copy, but of 0 and 1, but it cannot make a copy of alpha 0 plus beta 1 if it is going through the same mechanism as 0 and 1 were going. So in fact, you cannot clone an unknown quantum state. Of course, you can clone a known quantum state. You can just know the alpha and beta, and you can prepare a perfect copy without disturbing the original one. But you cannot clone an unknown quantum state, where you can do it for the classical one. Okay, so in fact, this is of advantage in some case, and of course, the sender and the receiver for the key distribution can utilize it. Then another property of quantum states is their non-orthogonality. Let's see what it is. So a quantum state, as I said, that quantum bit, it can exist in any possible state, like it can be any point on the Bloch sphere, and of which we have seen these 2 points. But the 0 and 1, for example, we can give any character, any state of a quantum bit to call it 0 and any to be 1, right? So it should be, a qubit should be just a thing that can exist in 2 possible states. So in fact, it can be anything. It can be like the polarization state of photons. It can be the spin state of atoms, of electrons. It can be any quantum object that can exist in 2 possible states, and the superposition of those can act as a quantum bit. So let's see that we talk about the polarization of photons, right? So this is the horizontal polarization. As you see, it allows only the light which is polarized along the horizontal direction like this. It will make a horizontal polarization. And this is the vertical polarization. So we call the horizontal polarization of photon to be the state 0, right? And in fact, call the bit value 0 as well to it. And the qubit value is the state 1, and the bit value to be the state 1, to be the bit 1, right? And then these are the bases. So these are the horizontal vertical bases, in fact, that are associated with this quantum state. So with this corresponding to, with this corresponding to the vertical, this corresponding to the horizontal. And if a horizontal state passes through it, you will get a horizontal state out of it in the end, and it will be like the horizontal one, which is like this, and you will get a vertical one. When it passes through it, you will get this one, which is a vertical one. So if you record the bit value, so it will be like this, and if you record the bit value, the bit value will be 0 for this, and the bit value will be 1 for this. So it's a quantum state, and you can if you make this horizontal pass through it, it will just give you the horizontal one back, okay? But there can be, quantum state can exist in some other state as well. In fact, as I said, that it will be a superposition of those. So we can choose another set, which is in fact non-orthogonal to the first one, right? Here we see that if something exists in the state 0, it cannot exist in the state 1, right? So which means that if I take an inner product of the state 1 and 0, I will get 0. Inner product of the state 0 and 1, we are getting 0. So something that can exist in state 0 or in state 1 cannot, state 0, it cannot exist in state 1, and the one who can exist in state 0 cannot exist in state 1, which means that they are orthogonal to each other, right? But there are only 2 possible orthogonal states because it's a 2-dimensional Hilbert space, right? So there are only 2 possible orthogonal states. There can be another set of orthogonal states, definitely, right? Which means that let's say that we choose, rather than choosing the horizontal and vertical polarization, we choose the polarization at an angle, right? We call it the plus state or the 0 bar state or anything. And here, our plus, we define it as 1 over under root 2, 0 plus 1, right? Which is this diagonal state, right? This diagonal in this direction. And there is another state, which is minus, and it is equal to 1 over under root 2, 0 minus 1, which is diagonal in the opposite direction. In fact, these 2 states, if you check them, these are orthogonal to each other. That is, if I do plus and minus, these states will be one. I will get 1 over under root 2, and I will get 0 plus 1. And I'm just taking the inner product of the two, and it will be 0 plus 0 minus 1, plus and minus, right? And 1 over under root 2 for that as well. So I'll get 1 over 2. Right, so I will have 1 over 2 over here, and this gives me 1 over 2, 0, 0, plus 0, 1. So with the minus sign over here, minus 0, 1, and plus 1, 0, and minus, which will be minus 1, 1. And so this is 0, 0. So this is 0, 0. And I have got half over there, and I have half. This is 1. 0, 1 in a product is 0. As we have agreed, they are orthogonal to each other, right? And then 1, 0 is 1, 0 is 0, and 1, 1 is 1, right? And this gives us 0, which means that plus minus are in fact orthogonal to one another. But these plus minus states are in fact, if you compare them with this, so if I take a plus with a 0, what do I get? So it is 1 over under root 2, which is 1 over under root 2, 0 plus 1. And I have an inner product with the state 0, right? This one. And this will give me 1 over under root 2, 0, 0, plus 1, 0. The second term is 0, but the first term is not equal to 0, and it gives me 1 over under root 2. So the plus 0 is 1 over under root 2, the inner product, which means that plus is not orthogonal to 0. And similarly, plus is not orthogonal to 1, and plus is not orthogonal to minus is not orthogonal to 0. So if I just write it over here, my plus 0 would be equal to 1 over under root 2, plus when I take an inner product with 1, I will get again 1 over under root 2. And if I take an inner product of minus with 0, I will get 1 over under root 2. And if I take an inner product of minus with 1, I will get minus 1 over under root 2. So their inner products, they are all non-orthogonal to each other, right? So plus and minus, though they are orthogonal with one another, they are non-orthogonal to 0 and 1, which means that actually we have two pairs of states, which are with two states which are in fact orthogonal to one another, but we have another pair which are non-orthogonal to the first pair, right? So we have two sets which are non-orthogonal to each other. And in fact, if I go back to the block sphere, we can see that these states are, this is 0 and 1, which are in fact the orthogonal states, and this one and the other one on this side, which is 0 minus 1 over under root 2 on the block sphere. These two are the plus and the minus states, right? This is the plus state, and this is the minus state. And these two are orthogonal to one another, plus and minus, but they are non-orthogonal to 0 and 1, right? So why we are interested in that, let's see. So we have two pairs, right, which are non-orthogonal to each other. And in fact, they are the basis set which make them. So the basis set of 0 and 1 is in fact the horizontal vertical basis, and these are the diagonal bases whose basis set consists of plus and minus. This is the basis set for this, which is the diagonal basis. This is the basis set of 0 and 1, which are the horizontal vertical basis, right? So we have come across two basis sets, 0 and 1, and plus and minus, and these two basis sets are non-orthogonal to each other, but the basis states within each set are orthogonal. Okay, so let's go ahead. Then when you try to measure a quantum state, then what will you encounter? So first thing is that you have to prepare a quantum state in certain direction, right? So again, let's consider the polarization. So you have a light source which has photons along the random polarization, right? They can exist in any, not just these four, but in any, right? And then you prepare one of the photon into one particular polarization direction. For example, you just put this preparation apparatus in front of it, which only allows the vertical light the light with the vertical polarization to pass through it. Okay. So when you try to pass this through when it passes through this and it is now going ahead, then you try to measure this state. So if you measure it with its bases, right, which were the horizontal vertical bases, which is this, if you try to measure it with the bases, of course, it will go in the vertical direction, and you will get this state again in the end, what you have measured, and you will record a bit value 1 from it, right? This is the bit value that you assign to it, and this is the bit value 1 that you will get in that. The quantum state will be in the state, which is the vertical state, which will be the which is in fact the one state that you have given, the vertical one. And but what if you have prepared it in one basis and you try to measure it with different bases? So let's suppose that the state that you prepared was this diagonal one, right? And it is the bit value 0, and it is the 0 bar, or it is the plus state that we talked about earlier. And this plus state is measured by the horizontal vertical basis rather than the diagonal basis. That is the basis of this basis set of which it belongs to, which is the plus and minus. So let's suppose that it was prepared by this diagonal one, but you try to measure it with the horizontal vertical. What would you get? So in order to measure it, this horizontal vertical basis in which you are trying to measure it will look at this state in its own basis, right? So first you have to write it in the basis of this measurement basis, right, which is the horizontal and the vertical. So just write the plus state or this in the form of the horizontal vertical, which of course we just talked about. It is 1 over under root 2, 0 plus 1, right, like this. So as we talked earlier, that if you try to measure a quantum state, which is in the horizontal vertical, which is in the superposition state, then there is a probability of alpha modulus square to get it in the state 0 and beta modulus square to get it in the state 1, which means that if you are, for this state, the alpha modulus square is half, which means 50%, and the beta modulus square is again half, which is 50%. So with 50% probability, you will get this vertical polarization, and with 50% probability, you will get the horizontal polarization. So you will record a bit value 1 with 50% times, and you will record a bit value 0 with 50% probability, right? So there is no definite answer to this measurement. While if you prepare and measure in the same basis, then you will get the same answer as the prepared state was. But if you measure it in a different basis, then your answer is totally random, right? It can be both 1 or 0. So which means what is the take-home message, which is this, that if the preparation basis, right, is the same as the measurement basis, the preparation basis is equal to the measurement basis, then, which is the first case, then the results actually match, right? Your measured state is the same as the prepared state. Then the prepared state, or in fact the measurement result that you get, measurement bit value that you get, so the measured state is the same as the prepared state, right? But if the measurement bases are not the same as the preparation basis, which means that what we are saying, that if the preparation basis is not the same as the measurement basis, then the results match only 50% of the times, right? As you say, you prepared the bit value 0, which was, you get the bit value 0 only 50% of the times in the end, right? And this is true for all 4 combinations, right? For all if you had prepared the horizontal one over here, it would have been the same result for this. You would have got the bit value 0, the qubit value 0, and the bit value 0 over here for the horizontal one. And the same would have been the case with the second one, right? So whenever the preparation bases do not match with the measurement basis, the results will match, the bit values will match, or results, which means the bit value, right? The bit value match only 50% of the times. Okay, so this is what we know if we use 2 sets of quantum states which are non-orthogonal to one another. So this is the principle on which the BB84 quantum key distribution protocol works. So let's just go back. Our aim is to distribute a key, right, which is totally random and which should be secret, right? And it should be, we want to distribute this key. So this D is for distribution, right? We have a key and we want to distribute it, which means that we want it to send to our legitimate user, which is the receiver, in such a way that it goes through the open channel, but anybody who is listening in between cannot just comprehend that what the actual key is, right? So let's see. So our aim will be to distribute this secret key through the open channel to the other legitimate user. So this is our sender, which is Alice. This is our receiver, which is Bob. And we have these 4 states that we talked about. So this is one basis set, right, that we talked about earlier, 0 and 1, horizontal and vertical. This is the other one, which is the vertical, which are the 2 diagonal ones. So this plus is the 0, is given the bit value. This is the plus 1. This is the minus. This is this plus is the given bit value 0. Minus is given the bit value 1. And this 0 horizontal polarization is given the bit value 0, and this 1 is given the bit value 1. Okay. So we then go ahead with our process. So first thing is that since the key has to be random, right? So we choose which bases to use first. So we have 2 basis sets, as I talked earlier. We have this 0 and, sorry, we have this 0 and 1 basis set, and the other one is this plus and minus, right? So we choose whether we want to use this basis set or this basis set, right? So first we toss a coin. For example, we toss a coin and we get that we will use this horizontal and vertical one. And then we toss a coin again, right? So we toss a coin again to choose whether we want to prepare our qubit in this state or in this state. And this all is done at the sender's end, right? So Alice is doing all this. So she first tosses a coin to decide which bases to use. Once the bases are chosen, she tosses the coin again to choose which one of the two states she wants to send, right? So when the coin is tossed and she gets the state 1, so she will prepare the state 1 with this preparation basis, and she prepares this state over here, right? So chosen, the bases are chosen, and the state is there, which is this 1 state, okay? And she records the bit value on her end, the bit value, right? So the thing that is going is the quantum state. It's not the classical bit. It's the quantum state that is going, quantum bit. It's in fact the polarized photon that is going. And she records the bit value on her end. The bit value is 1, of course, for this vertical one. So she records the bit value 1. And then she sends that qubit to Bob, right? So this qubit goes to Bob. Bob, on the other hand, has to measure this qubit. So he has 2 choices, right? So he doesn't know what Alice has prepared. He doesn't know which bases Alice has chosen. He doesn't know which state Alice has prepared. So he has to choose randomly, again, in order for it to be random, he has to choose randomly in which bases he will measure it. So he chooses, again, he tosses a coin. So now we are at the Bob's end, we are here, and he tosses the coin to choose which measurement bases he wants to use. So and we know that if the measurement bases are the same as the preparation bases, he will get the same bit value from our measurement process that we have learned. And if he uses the wrong bases, then his bit value will match 50% of the times. So which means that for this bit that we are using over here, this qubit, when it comes to the Bob's end, if he chooses this, his result will match exactly, and he will record the bit value 1. If, on the other hand, he chooses this, then his bit value there is a chance that it can be 1, but there is also a 50% chance that it can be 0, right? For this particular qubit that is coming over there. Once the qubit is measured, of course, it will be collapsed, and it will be collapsed into the corresponding state, right? So, but we do not care about that. We are just interested in our measurement result. And the measurement result we will record as a bit value. So let's go over here. So in this case, for example, so they do it for every bit, every qubit that is flying there. So for the first case, Bob, we are going to choose the Bob's detection basis and the Alice's preparation basis. So the first qubit that is here, Alice's preparation basis was the this orange purple one, which is the horizontal vertical. If Bob chooses this detection basis, the green blue one, which is the diagonal one, there is a possibility that he would have recorded the bit value 0 and he could have recorded the bit value 1, right? Suppose he records the bit value 0. He makes one single measurement, right? So it will be one value. So suppose he records the bit value to be equal to 0, which is this. And then for the second one, so for the second one, Alice has prepared it in the diagonal basis. She records the bit value 0 according to the sequence that they have decided. So this green has the bit value 0. Bob chooses the measurement basis randomly, and in this case, he chooses the right basis. That is the same basis as the preparation ones. So in this case, his bit value should exactly match, which is 0, right? The third case, this is the bit value 1 that Alice has recorded, and Bob chooses the measurement basis randomly. So it matches with the preparation basis, right? So both are the horizontal vertical, so they match, and his bit value should exactly match, which it does, right? He records 1. In the third case, let's look at the third one. The preparation basis exactly may match with the measurement basis. The bit value recorded 2 match. And in the third case, then again, the bases are different. So we see that this records 1. He could have recorded both 0 or 1, right? But suppose he makes a measurement and he gets 0. So let's look at the case where the bases do not match, but they record. So there can be a case in which their bases do not match, but still their bit values match, which is this last case. So for here, I should correct this, the bit value recorded 0, and this should be 0. Anyhow, this last one, this is the bit value. This is the bit value 1, and which Alice records. Bob uses different bases than the preparation basis, but he still records the value 1, right? Which coincidentally matches with it, right? Because there's a 50% probability that he gets the same bit value. Then now, so far, Alice has prepared the state on her end. Bob has measured the state on his end, and they do not know anything about each other, right? What Alice has made, what Bob has measured, they do not know. And they do not know about their basis choices as well. So what do? They announce their bases publicly, right? So this is the next step that they do, that the bases are announced publicly. So when they announce the basis, not the bit values, right? The basis, that whether they have chosen this, what were the preparation basis and what were the measurement basis. And they compare their basis. So we know, and they know that if their bases match, their bit values will exactly match. And in the case their bases do not match, then their bit values will match only 50% of the times. So they will discard, so they know exactly that where the bases match, their results actually exactly match. So they will keep all the cases where their measurement and the preparation bases match, right? So they are just announcing the bases, not the bit values. So they announced that the basis was this horizontal vertical, for example. It matches in the second case, they keep this bit value. It matches in the third case, and they'll keep this bit value, which is 1. And then it matches in the fourth case, they keep the bit. It doesn't match and they discard all the cases where the bases do not match. So they will discard the first case, their bases do not match. They discard this case is discarded, this case is discarded where the bases do not match, and this is discarded, this is discarded, and this is the case where the bases do not match, this is discarded. Their bases do not match in this one, so this is discarded, and I should not write it like this. Okay, so they discard this. Although there may be the case that their bit value may match in the case where their bases do not match, right? Which you can see that this is the last case. But actually they do not know whether their bit values match or not. Nobody knows that what the bit value is. They only know that whether they have used the same basis or not. And they are sure that wherever they have used the same basis, Alice and Bob, their bit values exactly match. But when they haven't used the same basis, there is 50% chance that their bit values will match. So although their bit values may be same in the cases where they have used the different bases, but they do not know in which one, right? So they discard all the cases where their bit values do not match. So they will be left with a bit sequence, which is this. So and they know exactly, right? So then they will tell they will know that keep the second bit, keep the third bit, keep the fourth bit, keep the sixth bit, keep the eighth bit, keep the ninth bit, and discard first, fifth, seventh, and 10th, right? So which means that they will be left with, in general, if you have very large number of qubits that are being distributed, they will be left with half the key length. Why? Because the bases are chosen randomly, right? So there are 50% times that their bases will match. And so 50% cases will be the ones in which their bases will not match. And so they will discard all the cases where bases do not match, and which means that they will discard the 50% number of the bits. The key string that is left is in fact key is half the original length, right? Which means that it is half the total number of qubits that have been shared. It is half the original length of the bit that was supposed to be there, right? Because half the cases have been discarded. But it's no big deal, because if you share a large number of bits, then it's you will still retain a large number of bits as your key. For example, you shared 10 raised to power 6, like 1 million qubits, right? And half the cases do not match. So which means that you will left with half of them, which is 0.5 into 10 raised to power 6, which is in fact equal to 5 into 10 raised to power 5, which is still a very large number, right? So if you start with a very large number of bits, you will be left, even after discarding half of them, you will be left with a very long string of key. So there are a few things in it. What were our requirements for the key? The first thing was that it should be as long as the message. So you can share any number of qubits in the beginning, and you can have the key which is in there. And the second was that it should be available, right? It should be used only once, and it should be there whenever they want to send a message. So they can do this thing. If they do not have the shared key before, they can employ this thing and distribute the key. And then once the key is there, they have done the sifting process, and they know that that they have the same key string. Then they will be able to use this key to encrypt the message using the Fermium cipher, right? That we talked about earlier. Because Fermium cipher is the only cipher that is mathematically proven to be secure. And we are trying to distribute the key which actually fulfills those conditions that we talked about earlier. So the problem is that, okay, we have done everything. We have a mechanism available to distribute the key at the time when we need it, right? And we are sending it through the open channel to anybody to the receiver. So the question is it secret, right? So this was our point, that we have to have the key should be secret in this case. So is it really secret? Let's see. So it is going through the open channel, right? So we assume that Alice is in her lab, Bob is in his lab, and the qubits that have been prepared are being sent to the Bob through the open channel. So Eve has no access to Alice and Bob's offices, but she has access to the channel from which the qubits are going. So this is Eve's territory in between, where she can in fact manipulate in any way the qubits, right? So let's just look at that, what Eve can do in this situation. So just look at a simple one, just to see whether it really is secret or not, and what could be done with it in the later one. So Eve can not access Alice and Bob's labs, but Eve can do anything in between. Now let's see that what if Eve merges too? So let's concentrate on the cases where Alice and Bob bases actually match and they keep the bit, right? So we do not consider the cases where the bases do not match, and because those are going to be discarded anyway. So let's suppose that Alice and Bob's bases match in this case. And so Alice sends the bit value 0. For example, this was the case, the one of the cases, that she prepares the bit value 0 or the quantum state 0 in this case, sends to Bob, Bob measures in the right basis, and he gets the right result, right? But what if there is Eve in between? Then Eve can also measure, right? But she doesn't know that whether Alice and Bob are, which bases Alice has prepared and which bases Bob is going to be used, because bases are announced when all the qubits have been transferred, right? And bases are announced in the end. All the qubits have been transferred. Bob has measured the qubits, recorded as bit values, and then the bases are announced, right? So let's see that. So Eve doesn't know when the qubits are in the channel. Eve doesn't know which bases were used for the preparation and which bases were used for the Bob. So she has the same two choices as Bob has. So she has to decide randomly which bases to choose for measurement. So let's suppose that she decides, she chooses the right basis, right? So it's random. So she chooses the right basis, which is this case that she chooses the horizontal and the vertical, sorry, the diagonal one in which it was prepared. If he uses the right basis, her result should exactly match with the Alice's result, right? Because she's using the same basis as the preparation one. So she will record the bit value 0. And so the bit value recorded is correct. Bob has recorded the same value. All three match, which means that Eve now has the same bit value as Alice and Bob. And when the bases are announced, she also knows that she has used the right basis, and she knows that her result, whatever it is, 0. She knows that Alice also has prepared the 0 and Bob has got 0. So she knows exactly the bit value. But this basis choice by her was totally random, right? She could have chosen the wrong basis. For example, she chooses the wrong basis, which is this one. So in this case, she again has two choices, right? She can record a bit value. So since she is not using the same basis as the preparation ones, so she has 50% chance of getting the bit value 0 and 50% chance of getting the bit value 1. So she will be definitely measuring the state 0 or state 1, but she is recording the bit value, which may or may not match. So when she records the bit value 0, her bit value is correct, and she sends the state to Bob. Bob, on the other hand, is now using, since this was the case when Bob uses the same basis as Alice. So he uses the same basis, but his basis choice does not match with Eve. Now his reference point is Eve, right? Not Alice. So since his basis choice does not match with Eve, so he will have, in this case, he will have two, the state prepared was 0 in this state, and he has the plus minus basis, right? The diagonal ones. So there is a 50% chance that with the wrong basis compared to this reference, which is now Eve, there's a 50% chance of getting the bit value 0 and 50% chance of getting the bit value 1. So his bit value will match only in half the cases in this case. But if if Eve gets the bit value 0, her bit value doesn't match, her answer is wrong. And Bob, again, it's not that his answer will be wrong, definitely, although he's still using the wrong basis compared to Eve, which is his reference point now. He's using the wrong basis, so there is a 50% chance that he will get the bit value 0, 50% that he will get the bit value 1. So in this case, as you see, whenever Eve's bases match, she knows exactly what the bit value is. Whenever her bases do not match, she has these two possibilities. And since in the end only bases are announced, she doesn't know that what the bit value is, which is totally random for her. So doesn't know means that even if she has 0, she doesn't know whether it is correct or not, although this bit value is correct. And not knowing out of 2 means that she doesn't know anything actually. She doesn't know whether it's 0 or whether her value is correct or her value is wrong. So she has no knowledge, she has gained no information in the case where her bases do not match, right? Which is this case. So in the cases where her bit values exactly match, she will have her bases exactly match, then in this case, she knows her bases match, she knows she's correct, and she knows that Alice and Bob have the same bit value. So she actually knows, she actually has the 50% knowledge, right? So she can do it on all possible combinations, and she will have, in each case, where Alice and Bob's bases match, Eve has all these possibilities. And in these cases, she has always the correct value and the right information in only the cases where her bases exactly match. This one, this one, this one in this case, and this one in this. So 50% of the times she knows exactly that what the bit value is. So Eve's information is in fact about the key. Eve's information will be 50%. But in the case that she has used the wrong basis, her basis value, the bit value, her bit, she has no information, right? And on the other hand, Bob's bit value may be correct, but he thinks his bit value is correct, but in fact it is not correct, which means that there is error in his key. So you can see that there is error in this case, that there is this zero over here, and there is in this case, you see that this is the correct value, this is the correct value, but these two are wrong. So out of all these cases, 1/4 of the times his bit value is wrong, where he thinks it should be right? So there is an error. So there is an error on the Bob side, which is 25%. So although Eve has gained 50%, although we claimed that we have a very nice protocol, which works very fine, there's a key that has been distributed. Eve has 50% knowledge about the key, and there is a 25% error in it. So what to do then? So in the next lecture, so this is what it is. So this is the situation. Of course, if there is an Eve and she is trying to learn what there is, she will gain 50% of the information in this simple attack. And she would have created error as well. So this means that the keys do not exactly match in this case. And Eve also has some knowledge. But Alice and Bob can still work on it, right? And this we'll do in the next lecture. That what if there are errors in the key? What if there's somebody is doing an attack on that, which is Eve, and we'll pick up from here, and we'll see that still we can make the protocol to be secure and to make the keys secret and to be distributed in the same way, like in this PB84 protocol. So thank you very much. So the next lecture will go ahead from here, that if there is a listener in between, there is some information gain, then how can we still go ahead with the protocol? So thank you very much for today's lecture. And any questions?